All right, so let's look at LEDs. So LEDs have a direction to them. Okay, LEDs are like one-way resistors. If you take an LED and measure it with a multimeter, if you hook the leads up to each end, sometimes you'll see zero resistance, sometimes you'll see infinite resistance. It depends on the direction of the LED. It's kind of magic. It's like a one-way valve. So current can flow in one direction but not in the other. And you can try this. Grab an LED, measure the resistance, and if it says zero, flip the leads around, measure the resistance again, it'll say infinite. Right? So it only lets things go in one way. So the way an LED is drawn, we have this triangle and a circle. The triangle shows the direction the current flows. So this is current flowing in this direction. So if we have ground over here, that's the end that should be at the point of the triangle. If we had 5 volts over here, then the LED will want to go in the other direction. We'll see that in Lab 3 also. Lab 3 is all about playing with LEDs and switches too. So when you put your LED in the board, you've got to make sure you've got it in the right orientation. Because if you put it backwards, current won't flow. And there's 3 ways to orient your LED. There's 4 ways. One is to use a multimeter. Okay, and that requires you to get a multimeter, which I don't usually have patience for. The second is to look at the side of the LED, and there's a side on on one edge that's flat. So your LED, if you look at it from the top, you'd think it would be a perfect circle, but in fact there's a flat edge on one of the leads. I can never remember which lead is flat though. It's either positive or negative. A third way is to look at which lead is longer. Okay, they have different lengths, so one is slightly longer than the other. I don't remember which one is which, and if somebody cuts the leads, that doesn't work anyway. So the other way to tell which is which is to hold it up to light, right, like a fine wine or something. And you notice inside there's a big piece of metal and there's a little piece of metal. Right, it's got this funny structure to it. The big piece of metal, that's ground. So whatever side that pin is on, that's the ground pin. The other side is the one that's positive. So if I was building this circuit over here, right, this end of the LED that's ultimately going to ground, that would come from this pin on the right. So a variety of ways to tell that. And the book tells you how to do it with the flat edge and with the longer, shorter pin.
Question about that.
Yeah.
That just looks like one big piece of metal.
This thing?
Yeah, I can't see the two.
Oh, that's also fuzzy. Yeah, you got to look at it closer, I guess. And if you look at a real one, you'll probably see what's going on. But this is like, on the right, there's a piece of metal going up like this, and it comes down.
Oh, okay.
And then on the other side, there's this. Except the one on the left is really short.
Okay, nice.
Okay, cool. All right, so switches and LEDs, good for now. Let's look at the homework. So homework first. So this is posted on Canvas. 20-point homework, right? Double points. And it's one question, but it's got several parts to it. Okay, and you want to write this up like all the other homeworks, as far as doing the parts in order and name and staple location, all that stuff. So what's the basic goal here? We're designing a circuit with 3 push-button inputs. And the push buttons are normally open, okay, and there's a single LED output. And here's the behavior you want. If you push any 2 of the push buttons, exactly 2, and leave one unpushed, we'd like the LED to turn on. Otherwise, the LED is off. So not touching anything, LED is off. Push just one button, LED stays off. Push all 3 buttons, LED stays off. Push the first and second buttons only, LED is on. Second, third, LED is on. First and third, LED is on. Anything else, LED is off. So 3 inputs, 1 output. And we want to ultimately design a circuit and make a full logic diagram with part numbers and pin numbers and switches and LEDs for this behavior. All right, so I'm giving this to you in pieces. So step A is to just think about the push button. So if push button is normally open, right? So when you don't push it, it's disconnected. When you push it, it's connected. Okay, so sketch a circuit, and this is not going to have pin numbers or part numbers on it, okay, because it's just a switch, resistors, power connections. But sketch a circuit with those components, okay, something like this, something like this. All right, in the one correct way we've described in class. And then indicate clearly what the output will be when the switch is pressed and when it's not pressed. So draw something like this, and if the switch is normally open, what happens when it's not pressed? It's open, it's disconnected. What's your output going to be? Right? So in this case, it would be 5 volts, logic 1. If the button is pressed, since it's normally open, pressing it closes it, this gets closed. Your output's going to be 0 volts, logic 0. Yeah?
So we have to make some kind of like, so yeah, make a diagram, but also make like an equation.
You could write it like an equation, but here I'm really just trying to get you to think about the behavior of pushing the button or not pushing the button in terms of the output. Yeah?
Are you asking us to draw 2 for like when the output's 0 and the other output's 1?
It's one circuit, but I'm asking you to consider 2 cases. Okay, so the punchline for part A, indicate clearly what the output will be when the switch is pressed and when it's not pressed. Yeah?
Are we trying to use optimal resources? Because if I really like thinking of push down as a 1, I could put a not or an inverter there. But
Yes. But I want you to use a normally open.
okay.
And it's going to feel backwards. If you do the analysis correctly, it's going to be a little bit counterintuitive. Okay, which is why I'm specifically asking you to do this as a separate step. Okay, so don't just trust your intuition and say, okay, if I push it, it's a 1. If I let it go, it's a 0. Okay, go through the analysis and you'll see exactly what it does. And my note here is that this kind of switch is going to pop up again and again and again. Right, so the sooner, the earlier you get comfortable with how it behaves, the better off that's going to be. Okay, part B, draw a system diagram for the entire circuit that we're after. Okay, this thing with 3 buttons and 1 LED. It's just a box with 3 arrows going in, 1 arrow going out. But I want you to think about how you're going to label these things and what you need to specify. What does it mean when an input is a 1? Does that mean the button's pressed or it's not pressed? Well, you're going to find that out in part A. Okay. What does it mean if the output is 1 or a 0? Since we're using an LED, if we're using an LED that's going to be connected to ground like this, a 1's going to turn the LED on, a 0 is going to turn it off. But you could do this differently. You could connect this end to 5 volts, and what you'll discover in lab 3 is if you put a 0 in here, the LED would turn on. If you put a 1, it'll turn off. So make sure that's specified somewhere in your system diagram, usually just a few lines right below it. What are the inputs? What are the outputs? Okay, another suggestion here. The inputs should be labeled with single letters. Don't call your input button 1, button 2, button 3, because you're going to write equations using these inputs. And writing an equation like button 1 or button 2 is more confusing than A or B, X or Y. So label your inputs with single letters. Your output can be more complex if you want, because that's going to be on the left side of an equation. All right, in C we move to writing a truth table based on the description of our circuit, which is if 2 buttons are pressed, the output should turn on the LED, and so on and so forth. Turn that into a truth table. Okay, use the same variable names that you used in your system diagram. So if you called your inputs A, B, C in your system diagram, don't call them X, Y, Z in your truth table, because you want these to be related to each other. Okay, so come up with a truth table and double check the behavior of it. Make sure after you've got your truth table, looking at everything you've done so far, if I push these two buttons, what are my input values? What does my truth table say the output is? Okay, and if you're not sure if you got it right, just ask. All right, now it becomes more mechanical. Once you have a truth table, write output equations. So you've got inputs, you've got an output. Output equals some combination of inputs. Yeah?
So I was thinking in my head that if I make a truth table, and if I make these two inputs on, then the output will be on. And if I do that along the way, then I might be able to figure out what diagram I want to use.
Mm-hmm.
Unless that I usually do it, because all of a sudden I popped in my head thinking, oh, now I know how to do this.
I think what you just said was right. So the truth table captures what the circuit's supposed to do. Right? So anytime the two buttons are pressed, that corresponds to some combination of input values. And for each of those combinations, you want your output variable to be a 1.
And also, is it a good idea to use a K-map to try to simplify it?
Yes, so when you write your output equations, make those as simple as possible, unless you really like drawing complex circuits. But I would suggest minimizing those. And one way to do that is with a K-map. So if you do that, right, follow, the original equations or the truth table or something with the K-maps, lay those out, right? Remember, we're working top to bottom, don't go across the page, and label everything and circle things that need to be circled and so on and so forth. And at the end of step D, you should have a nice equation for, output LED equals blah, 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 some logic equation involving your input variables. And then part E, draw a circuit to implement that equation. Okay, again, only use the components that are on the website, and be sure to include part numbers cross-referenced in the component ID block. So U1, U2, U3, and in the component ID block, right, list each thing, where's the power, ground, all that stuff from last Tuesday. A project ID block, lower right, that has your name, the date, and a couple of words describing what the circuit is. Homework for a circuit, something like that. Part numbers on all the gates, so label your gates U1, U2, pin numbers on each input and output to the gate to show what things are connected to what. And make sure you have switches and LEDs. All right, so that's a fair amount of writing. Yeah.
So what is the logic supposed to be? Like, are we supposed to be is it supposed to be like an out, right, and or?
Up to you. So if you do a sum of products and you reduce it with a K-map, you should get a fairly simple equation. That's not too many things to implement. If you do a product of sums, you may get some really horrifying equation. And we're going to get horrifying equations in lab 3, so we'll get some practice on that. But yeah, whatever's going to implement it, just make sure that as you're working through, right, everything flows. So if you write your truth table and you write your equation, and your equation is this, and then there's some circuit that has nothing directly to do with the equation, then something's missing, right? So if you simplify your equation, make sure you show that simplification and you circle what the final equation is, and then in the next step you actually design a circuit using that equation, right? Then it's easy to sort of follow how you got to the final answers. And don't hesitate to ask me about this, right? Not like an hour before it's due, but maybe Tuesday or Monday. You can come to office hours, or you can catch me during class, or you can ask in class, right? Is this what you're looking for? Is this enough detail? Does this make sense? I don't know how to do this, whatever. Okay, because my goal is not to test whether you can do this, right? My goal is to help you figure out how to do this. So feel free to ask. All right, other questions on this? Cool. All right, let's look at lab 3. All right, so lab 3 is all about sums of products, product of sums, minimization, things like that, and switches and LEDs. So there's some quirky experiments in here, and then the last part is a lot of writing, a lot of thinking and writing. So experiment 1 is about LEDs. Okay, so here it tells you the short lead is negative, the long lead is positive. All right, experiment 1, you're going to build 3 circuits. Okay, here's your first circuit, here's your second circuit, here's your third circuit. So your first circuit, 5 volts, goes through a 1K resistor, goes through an LED, goes to ground. Second circuit, low, that means logic 0, so that's ground, goes into an inverter. Output of the inverter goes through an LED, goes through a 1K, goes to ground. Third circuit, high, that's logic 1, that's 5 volts going through a resistor, goes into an inverter. Output of the inverter goes into the end of the LED, and the other side of the LED goes through a 1K, and that goes to VCC, 5 volts. So 3 different circuits, and it can be convenient to sort of build these all kind of like side by side on the same proto board, because what you want to do is observe what these circuits do when you power them, and also compare them to each other. Yeah?
Is there any reason in configuration 1 you couldn't put the 1K ohm after the LED?
You could.
Okay.
And it should do the same, and if you want to do that, that could be a cool thing to note. I would build it exactly like this though.
Okay.
Just because theoretically maybe it makes a difference, but it would be cool to put it after and then compare the results. All right, so set up the following 3 configurations and record your observations, explain any observed differences. So in the lab reports, when I said to have observations, I'm talking about, observing what it is that you're doing, as opposed to maybe reflections, where you could say something like, this was a rehash of stuff we did in 120, but it was useful because I'd forgotten a lot of stuff. That's like a reflection, right? Which you can put in your report, but for observations, I'm looking for what did you see, what did you measure, what did you observe? So this could go in an observation area, right? So procedure, so introduction might be, experiment 1, we looked at different ways of hooking up LEDs. Procedure would be we built 3 circuits using the configuration shown in figures 1, 2, and 3, or figure 1, right? We applied power and then we observed what happened. Observation would be configuration 1 lit up in green, configuration 2 exploded, configuration 3 started blinking Morse code, which I translated to a message from aliens. Okay, so whatever you observed. Oh yeah, let me make another comment here. So everybody who has taken pictures from the lab so far has mentioned that they came from the lab, which is excellent. Okay, that's like really, really, really super important. Because if you accidentally put a picture into a lab report that's not yours, you can get into serious trouble. Right? I had a friend who got into really bad trouble for that. So everybody's been saying this is taken from the lab, or this was from the assignment, or things like that, which is awesome. So I'm going to up the game now. I'm going to say, when you take figures from another source, right, anything that you're not creating yourself, so whatever, right? I'm going to ask you to put a note right below the figure and say something like this, image or figure from, and list exactly where it came from, but put it right below the picture, so it's kind of part of the picture. Okay, image from such and such. And for most of this is going to be an online source. So from https engrcs.com/ blah 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 blah. Right? And since it's an online source, add something which says accessed and put down the date that you did that download. So 25 April 2019. And let's see if we can put that on every figure that comes from a source. And this is an acceptable one way to do references in a professional paper. Written references, you normally see something like a pair of brackets with a number inside after certain sentences, and that refers you to something called a bibliography. And the bibliography says, where did this thing come from? And there's tons of specific formats for that, right? Lots of different standards depending on what subject area you're publishing in. So this is the standard we're going to use for this course. Right, so right below the picture, just say, you know, figure from or picture from or image from, list the source, and if it's online, put down when you accessed it. Does that make sense? All right, cool. So, so those are the circuit configurations. So yeah, obviously put those pictures somewhere, or draw pictures to capture this somewhere in experiment 1. All right, experiment 2 is about playing with switches, and you're going to build this crazy circuit. So there's a switch over there on the left, goes through a 1K up to power, we've seen that. The other end of the 1K goes into an inverter. The output of the inverter goes to an LED, 1K and down to ground, that's called L2. The output of this inverter also goes up through another inverter, whose output goes into the pointy side of an LED, L1, goes through a 1K, goes to 5 volts. So this is kind of a crazy circuit, but when you open the switch as it's shown or close it by connecting these two sides, things will happen on the LEDs. So set up the following circuit and complete a truth table relating the switch setting and status of the LED. Use the assigned 1, 0 values for switch setting and LED status. So the switch, if it's open, we call that a 1. If it's closed, we call it a 0. The LED, if it's on, we call it a 1. If it's off, we call it a 0. My suggestion here, make 2 truth tables. Make your first truth table using the words open, closed for the switch, on, off for the LED. Right? And just observe it. Leave the switch open, see if the LEDs are on or off. And then translate open into 1, closed to 0, on to 1, off to 0. The reason I suggest 2 truth tables is because a lot of times the transition from what you observe to putting in the 1s and 0s, something flips in people's brain. And your truth table comes out backwards.
What if I explained before that 0 represents closed and 1% open for the switch? If I explain that before I explain it, before I actually show the result of the truth table, that way that if someone reads it, they won't be confused about like what 1 0 represents.
Yes, so it's good to put that in your write-up, right? But ultimately you want a truth table with 1s and 0s.
And explain that 0% closed for switches and 1 is open, so that way I don't write 2 truth tables and list both on.
Like I say, the only reason the only thing that I require is, what do they call the switch here? Switch. So switch L1, L2, 0, 1, and fill in those values. That's what you need to have for the report, right? So these are 1s or 0s. And you're going to observe, I'm going to close the switch and this light's on and this light's off. And I'm going to open the switch and this light's off and this light's on, or whatever, right? You're going to use that to create this table. All I'm suggesting is whatever process you go through, if you document that, will help if something goes wrong in that process. If you're absolutely sure that the 1s and 0s you're putting here correspond to what you saw, just fill in this table. But historically, probably about half the reports I get, they'll say, when the switch was open, such and such happened. And then I look at the truth table and it's got the wrong values. And so it's like, okay, so what did you actually observe, right? So if you make a truth table that says switch is open, lights are on, switch is closed, lights are off, right? Up to you. Best option, just don't make any mistakes. But in lieu of that, right, show me your process for getting to that table. All right, so that's experiment 2. Build this circuit, power it up, put the switch in its 2 positions, see what the lights do. And you can always talk about this, right? I don't think it actually says that you need to discuss this, but there's a section for discussion in the lab report following each experiment. You can be like me and just build this and make the truth table and then forget about it, right? Or you can be a better student than I was and talk about it among your group members, right? Does this make sense? Why is this happening, right? Why did the lights do such and such when the switch did this thing or that thing? Does it make sense? And if it's not clear why this happened and you think about it and you figure it out, you can put that in your lab report, right? Think of this as, something that you're doing and you're going to put this out in the general scientific community to enrich other people's understanding of switches and LEDs. All right, experiment 3, guess what? Traffic control signal system. So here we go. This is going to be long, okay? Experiment 3, this is the most work you're going to do in any experiment in this course, except maybe lab 6. You're further developing the design of your traffic light control system. You did a design in lab 2. But we've learned about sums of products and product of sums and minimizations and so on and so forth. So here's what you're going to do for experiment 3. The usual, sketch the intersection, make a system diagram, right? Explain your variables, all that stuff you can take from your prior labs. Truth table for outputs in terms of inputs. Okay, that gets us through the first 2 parts. Part C, using a sum of products approach. So you have a truth table, you know how to write a sum of products. You're going to write a non-minimized sum of products for each light. Okay, this will be less writing if you only have 1 output per light. And you use this idea of 1 is green, 0 is red. So then you only got 3 outputs. If you do 6 outputs, 1 for the green light, 1 for the red light on each lane, right, you're going to have more work to do. But up to you. But your goal is to write an equation for each output in terms of inputs using sum of products, okay, min terms, without minimizing. And I want a full sum of products representation here, not just M1 plus M2 plus M4. Okay, I want you to actually write out the logic expression. So you've got your equations, you've got your truth tables. Go ahead and draw a schematic from that. Okay, using logic gates available on the website, part numbers, pin numbers. It's going to be a fairly big schematic. And then part D, same thing but do product of sums. So take the truth table, find the zeros, write down the expressions for the max terms corresponding to those, multiply those together. Don't simplify it. Take that to draw a logic diagram, find parts from the website, make a component ID block, assign part numbers, put the part numbers on the gates, put the pin numbers, come up with a full diagram. Okay, that one's going to be really big. Typically it's 2 sheets of paper. And if it's really big, right, try to do something other than just shrink it down so it's impossible to read. Do something like, have 1 sheet for 1 section, another sheet for another section, and draw a letter where you're connecting a wire from 1 sheet to another, right? Or something like that, because it's got to be something that we can read. Okay, so part D, you're probably going to get a pretty big circuit. Part E, you look at the two circuits that you came up with, and you decide which one would I want to actually build. One of them may have a lot more parts, one of them may feel more natural. This is very subjective. Most people end up wanting to build the sum of products. But take a look at the two designs and think about it and talk about it in your report. And make a decision which one are you going to implement. So explain which one is the optimum design that you recommend for implementation and why. So that's part E. Okay, part F. Let's say you decided you're going to implement the sum of products. So part F, now what you do is you go ahead and you minimize the equations for the sum of products. So use your K-maps to come up with minimized equations and then redraw the schematic based on those minimized equations. If you decide you're going to do product of sums, same thing. Use K-maps, minimize the product of sums, and then redraw your schematic. So you're going to have three schematics in here. You're going to have the unsimplified sum of products, unsimplified product of sums, and then the simplified version of whichever you choose. Everyone clear on that? Three schematics, just for experiment 3. Okay, and then once you have your simplified schematic, build it. Okay, so get a proto board, get some chips, get some wires, put it all together. Switches for your inputs, LEDs for your outputs. All right, and then once you've built it, you're going to test it out, and once it works, you're going to demonstrate it to me or whoever is in the lab. You can find Izad, anybody who's floating around, you can grab them and demonstrate it and get them to sign off. And you want a written test plan to help demonstrate that this works. So let's talk about test plans. This last sentence here, it's important that you have a written test plan with step-by-step process validating that all system requirements have been met. Okay, this is all about sort of delegation of responsibilities. Okay, you're the high-paid engineer, you come up with the design, the truth table, the equations, the circuit, you turn it into a wiring diagram. You hand that wiring diagram to somebody and they build it. Right? And they don't need to know anything about K-maps or product of sums. They just need to know 74LS04, that's this chip, pin 1 is right here. And they follow the pin numbering and they build up the circuit. Okay, they finish the circuit, they hand it to somebody else who's going to test it. And they don't know anything about wiring diagrams or K-maps or product of sums or anything else. So how are they going to test your circuit to know if it works or not? They're going to follow a test plan. So what's the test plan? It would say something like, take switch 1 and put it in the open position, and put switches 2 and 3 in the closed position. And LED 1 should be on, and LED 2 and 3 should be off. And now put switch 2 in the closed position and 1 in the open, and now LED 2 should be on, and LEDs 1 and 3 should be off. And you describe in a written plan all the steps that should be followed to validate that this circuit works. So you think about all the different test cases, and if it had a lot of inputs, you wouldn't go through every single possible combination of inputs, but you want all the ones that are going to test all the important features. So coming up with a good test plan, that's a whole art in itself. Okay, that's what my dad spent his life doing. It's coming up with test plans, doing system quality engineering. So you got to think about that. How do we test this thing? Now we've only got 3 inputs here and 3 or 6 outputs. So it's pretty feasible to go through all the possible combinations. But don't just write a truth table and say, make sure the circuit does this, right? Because the person you're handing this to, they don't know truth tables, right? They can read written instructions and they can follow them and they can say, did this happen or not happen? So, you know, turn these 2 switches to 1, turn this switch to a 0, right? Open, closed, whatever. Make sure this LED is on and these 2 LEDs are off. So written test plan, right, I suggest a set of numbered steps, maybe put a little checkbox next to each one. And then as you go through this, you could check off each box, and when you get to the end of the test plan, if all the boxes are checked, your circuit passed. Okay, so when you're demonstrating this to me or to somebody else, you should have this written test plan beside your circuit. And it should be written in such a way that the person that you're demonstrating this to could actually do the testing themselves. So they could go in and they could flip the switches and they could look at the LEDs and they can say, okay, that test passed, and so on. Is that clear what the goal is there? And you don't have to make the person do it. You can do the tests for them, but they might choose to run through your test plan yourself. If it's me, I'll probably run through your test plan myself and check the boxes. And then at the bottom of the test plan, have a line for a signature. And whoever you're demonstrating it to, once they agree that you passed all the tests, they can sign on that line, they can put the date there, and you include that signed test plan in your lab report. And that confirms to whoever's using this that your circuit actually worked. And something to that effect is going to be a part of most of the labs going forward, this course and 270. So it's a thing to get into practice of, and it's a standard practice in the industry to do a validation like this. All right, so parts C, D, and E you can do at home. You don't need to be in a collaboratorium to do that because that's all stuff that we've been doing, right? Writing truth tables, converting them to equations, stuff like that, drawing circuit diagrams. And everybody in the group should do this, right? Don't just say, okay, you're going to draw the circuit diagrams, I'm going to do the test plan, and you're going to build the circuit. That's probably not a good way to do this because you want to be able to do these things on tests and stuff. And so this is a good chance to get experience with it. So everybody should come up with their own equations, diagrams, decision about what to implement for C, D, and E. When it comes time to actually implement, you can get together and argue your cases. If you came up with different ideas of what to build, right, you can decide as a group which one you're going to build, or you can go rogue and everybody builds their own circuit. But usually people make a consensus, and so on. All right, questions on that? Main thing to stress is it's a lot of writing, so plan on spending some time on it. All right, wow, we still got time left. That's cool. Well, we were talking about adders last time. We talked about half adder, full adder, ripple carry adder. We talked about adding just by doing pencil and paper, adding right out the truth table and so on. So we looked at lots of ways to do addition. I mentioned that addition is important because it's the key to multiplication. And fast computers, we always want to do multiplication with them. So fast addition is important for scientific computation in particular. So what about subtraction? And somebody asked about doing subtraction, I think it was you. And we can build a subtractor circuit. You can build a half subtractor and a full subtractor and cascade them just like we did with addition. But we don't need to because we have this trick that we call 2's complement. And with 2's complement, we can calculate A minus B by actually calculating A plus the 2's complement of B. So we change B into a negative number and then we just do addition. So imagine that we have an adder. And let's just say it's a 4-bit adder. So we'll add the numbers A and B. Let me label these down here. And there's 4 sum bits. And there's a carry out, which I'll just think of as a 5th sum bit maybe. So there's a plain old adder, 2 4-bit numbers, and we get a sum out of the bottom. And suppose we want to use this to calculate something like A minus B. So we need to convert B into its 2's complement. If we made some circuit up here that changed B into its 2's complement, then this adder would calculate A plus negative B. That would be A minus B. There's your subtractor. So let me make some magic circuit up here. I should have made this a bigger magic circuit. This is why you use pencil. So we're going to actually put the number B in the top of this. A's are still going to come in here. We're going to put B in the top of this box, and what comes out of the bottom should be the 2's complement of B. And if we can make that happen, then this output down here is actually A minus B. But sometimes you want to do A plus B, so we're going to put something into the side here, which I'm going to label add slash subtract. Actually, I'm going to label it subtract add. Well, what does that mean? That's a weird way to label an input, so I'm going to tell you what this means. If I put a 1 in here, then we're going to calculate A minus B. If we put a 0 in here, we're going to calculate A plus B. So this is a really, really special magic circuit up here. If we put a 0 in, it's just going to take B from the top and pass it down to the bottom. But if we put a 1 in here on the side, it's going to take this B that's coming in the top, and we'd like it to generate the 2's complement of B on the bottom. So that now our adder is calculating A minus B. Well, that's our goal. Let's see how we can do that. How do we calculate the 2's complement of a number?
Invert and add 1.
Invert and add 1. Well, let's just worry about invert first. What we'd like to do is if we put a 1 in here, we would like to invert each of these bits coming in. And if we put a 0 in here, we'd like to not invert these bits. So we could use a NOT gate. And what we're looking for is some kind of gate. Right, that gets us an invert, but it always gets us the inverse. What we'd like to do is be able to control whether we get this behavior or we just get this behavior. So let's make a truth table. Let me call this S, because I don't want to write sub/add in a Boolean equation. So let's write a truth table for this. If my input S is a 0, then I want to do addition. So if my input S is 0, I want my circuit to act like this. I want to just take whatever the input B is and pass that to the output. So if S is 0 and B is 0, I want an output of 0. If S is 0 and B is 1, I want an output of 1. But if S is a 1, that's when I want to do subtraction. So I'm going to want to calculate a 2's complement. So if S is a 1, I want this circuit over here. So this is S equals 0, this is S equals 1. So if S is 1 and B is 0, I want an output of 1. If S is 1 and B is 1, I want to invert that, get an output of 0. So there's a truth table for this magic block. And what does this truth table look like, logic-wise? That's a good old exclusive OR. Right? It's an OR, except in this case where both inputs are 1, it goes back to a 0. So this is simply the equation output equals our subtract signal XORed with our input. And this is one way to think of what an XOR gate is. It's a selective NOT. It's a gate that if one input is 0, the other output matches that other input. But if this input is 1, the output is the opposite of this input. So it's a NOT gate we can turn on and off. So here's what we're going to build. We're going to make some exclusive ORs. And we're going to feed these input Bs into one side of the XORs. And the other side, we're going to connect all of these inputs together. And that's going to come from our subtract signal. Now we got a bit of magic going. If my subtract is a 0, the output down here is exactly the same as the original input. And I'm going to feed that into an adder. And my A's I'm just going to sandwich in here. Not going to do anything with those, so those come from some outside source. So if my subtract signal is a 0, this produces A plus B. And I'm going to use this funny shorthand. I'm going to draw a line with a slash and a number 4 next to it. That means I've actually got 4 lines coming out here. This is what we call a bus. So it's just a collection of lines. Alright, but if I want to do subtraction, I'm going to set subtract equal to a 1. These are all going to be the complement of the inputs. So I have the inverse of B coming in here, and I'm going to take A and add the inverse of B. Well, that's not quite the 2's complement. I've still got to add an extra 1 somehow. Any ideas how to do that? Full adder. Remember, when we designed this adder, we put a half adder down here because we said the incoming carry is always 0. If we simply allow an initial carry in to this adder, that's a way we can add 1 more to our sum. And what value do we connect to that carry in? We just add our subtract signal. So think about this now. If subtract is 0, the output of this block is exactly just B. A 0 goes into this carry in. This is just a plain old adder. This is just A plus B. If subtract is 1, these XORs invert B, so this is the inverse of B. The output is here is A added to the inverse of B, plus we're going to put a 1 to this original carry in. So it's A plus the inverse of B plus 1, that's A plus the 2's complement of B, that's A minus B. So that's a fully bona fide 4-bit add subtract unit. And to build it took nothing more than a plain old adder and a row of XOR gates. And this is an example of modular design. So how many people here have done programming? Oh, cool, awesome. So when you program, if you write more and more complex programs, you start trying to reuse old pieces of code. If you have a piece of code that does some particular thing and you want to do something similar to that, rather than write another piece of code that does almost the same thing, you try to make this general. Maybe you pass an argument to it to say, should I do this or that? Right, so code reuse. Well, we can do the same principle with hardware. We can have hardware reuse. So here's an adder we can also use as a subtractor by just adding a little bit more circuitry to it. And the adder might be very complex, right? But this extra circuitry is just a bunch of XOR gates and some wires. So that's good code reuse. And this unit we could use as part of a multiplier or a divider. because multiplication division involves addition subtraction. Well, rather than make another adder subtractor, we could just use this hardware inside it. And now we're down a path that would eventually lead us to designing a computer. Because what's a computer? It's something that basically decides what hardware to use on what operands based on a program. And a program is just a bunch of ones and zeros, kind of like what we're putting into here. So if we have an instruction in our program that says, let's do some subtraction, that instruction could somehow turn into a logic 1 signal that would go to this wire right here, and now your two numbers get subtracted. And the further you go down this road, the more you start to get the feeling that hardware and software are really the same thing. And at some point you've gone so far down the road of hardware development, you find yourself sitting in the middle of a software field. And you realize like they really are the same thing. And that's wonderful and horrifying. Okay, so that's a way to design a subtractor using an adder. And it's part of a theme that we're going to start building on, which is looking at how we can make things out of other things. Big things out of smaller things. So questions on that? We got 6 minutes left. I'm just going to keep like putting stuff out there. This is stuff in chapter 9 of the text now. Okay, so this is this thing that we jumped to. And well, let's breathe. Let's just talk about chapter 9 for a minute. I don't want to give you new stuff. So XORs we've talked about, adder and subtractor design we've talked about. Let's look at arithmetic logic units. So this is a chip you can buy, 74LS382. It has two 4-bit inputs, A and B. It's got that slash, 3-bit inputs. It's got that slash with a 3, which says there's actually an A0, A1, A2, B0, B1, B2. So this is this bus that we started talking about. And 3 output bits, F0, 1, and 2. So 2 inputs, 1 output. And does this add, does this subtract? This does a lot of different things. It's an even more extensive version of that circuit we just sketched out. This can do 8 different functions. And instead of just a single input that says should we add or subtract, you have 3 inputs to choose what this block will do. So these are called S0, S1, and S2, and depending on the value of those 3 inputs, you get one of 8 different behaviors. For example, if my inputs are 0, 0, 1, that's the second row, then F is equal to B minus A. So it'll take B, it'll subtract A, and it'll give us that 3-bit difference out on F. If my input on my select is 0, 1, 0, this will do A minus B. So it's subtracting in the other order. If our input on the select is 0, 1, 1, the output of F will be the sum of A and B, A plus B. If we want to do a logical AND on our inputs, we can set our select to 1, 0, 0, and the output will be A ANDed with B. So each bit of A gets ANDed with the corresponding bit of B, and you get a 3-bit output. So this can do 8 different things. It can do addition, it can do subtraction in both orders, it can do ANDs, ORs, XORs. I can say set my select to 0, and it will force the output to be all zeros. That's the clear output. I can set my input to 1, 1, 1, and it will force the output to be all ones. That's the preset behavior. So 8 different functions, which is kind of cool. So this is called an arithmetic logic unit, and you find these deep inside the hardware of computers. Because computers are always adding, subtracting, doing logic operations, things like that, and they use a piece of hardware like this. if you look at your components, I think we have a bigger one out here. Oh no, that's the 382. There we go, 74,181. So yeah, so this is what's inside one of these arithmetic units. All right, they didn't put pin numbers on. But this has 4 function selects, S0, 1, 2, and 3, 4-bit inputs, 4-bit outputs, plus a carry. And it only costs $5. And it's a big chip, 24 pins. They're fun to work with. And there's what it does. So depending on the value of your 4 selects, it can do a complement, A-1, it can do NANDs and NORs, it can do XORs, XNORs, various arithmetic operations, addition, subtraction, and so on and so forth. And you build CPUs around things like this. So the old VEX processor, a 32-bit machine, had 8 of these things inside, 4 bits each. 8 of those gives you 32 bits. That's how it added and subtracted. So we don't actually like build a general purpose computer in this course, but by the end of this course you've done enough and seen enough that you could probably do that. Right? We'll certainly go over all the pieces that go into something like a general CPU. And then in 270, when we start working with a microprocessor, that kind of ties up all the loose ends, and by the end of that, you probably have a pretty good conceptual idea of how these things actually work. And laptops, smartphones, mice that have processors inside, right? The underlying architecture hasn't changed in, I don't know, 70 or 80 years. It's the same basic architecture that von Neumann and company came up with back in the 20s and 30s. So this is, you know, what our world is made of today. So this will be generally useful stuff. All right, so work on the homework, think about the labs, bring questions on Tuesday definitely, if not before. And we'll keep working through Chapter 9 next week. We'll look at multiplexers, demultiplexers, some other things. And then we'll come back to starting looking at glitches again and timing, propagation delays.
So so on experiment 1 for lab 3, what does the L and the H mean again?
Low, L is low, which is 0, so that's connected to ground. H is high, that's 1, connected through a resistor to 5 volts.
Wait, so you're asking us to like create a circuit, I mean a kind of a basic circuit that has both ends connected to the same thing, because I noticed that.
Yeah, in some cases.
Oh, okay.
Yeah.
All right.